In this video on chapter 14, we're going to talk about polar and spherical coordinates. So let's look at this graph of the point xy in the usual rectangular coordinate system, and let's convert that coordinate to polar coordinates. So let's drop the perpendicular from the point xy to the x-axis. Let's label this angle theta. Let's call this distance from the origin to the point xyr. This side of the triangle here, the opposite over the hypotenuse, is going to be, or excuse me, it's the opposite side. We know that the sine of theta equals the opposite over the hypotenuse, which in this case is the opposite over r. So if we solve that for the opposite side of the triangle, we get r sine theta. And so we can call that side of the triangle is also the y-coordinate, and correspondingly this side of the triangle on the x-axis is the x-coordinate, so x is r cosine theta. So notice that if we square x and we square y, we get r squared. We get r squared cosine squared theta plus r squared sine squared theta. We factor out the r squared. That leaves cosine squared theta plus sine squared theta, which equals 1. And so the relationship between x, y, and r is that x squared plus y squared equals r squared. We can also get two other relationships. From either of these, we get a relationship between theta and r. So here theta is the inverse, well, if we divide both sides by r, we get x over r, and then take cosine inverse. So theta is cosine inverse of x over r, and also we have that sine inverse is, or theta equals sine inverse of y over r. If we divide these two expressions by each other, so if we divide these two expressions by each other, divide the y expression by the x expression, we get y over x equals r sine theta over r cosine theta. The r's cancel, and we get y over x equals tan theta, which gives rise to this other relationship for theta. Third relationship between theta, or a third way to get theta. So this way gets us theta just knowing y and x, whereas in these two relationships here we need to know either x and r or y and r. Polar coordinates are useful for drawing certain kinds of functions that would be pretty much impossible to draw in rectangular coordinates, or certainly to express in function form. So if we look at one of those functions, when we draw a graph of a function expressed in polar coordinates, we plug in, or typically plug in theta values and find the corresponding r values. So if we plug the angle theta equals 0 in, and we plug in 0 here, cosine of 0 is 1, we get a times 1 plus 1, so we get 2a for that value. And so if we plot that point, let's assume that distance is a, so there's the point at the angle 0. Then if we plug in the angle pi over 4, the cosine of pi over 4 is square root of 2 over 2, so we have a multiplied by 1 plus square root of 2 over 2. And 1 plus square root of 2 over 2 is approximately 1.7. So this is, let's put in 1.7a, even though that's only approximate. So we have the angle pi over 4 drawn. We go out a and 2a, but we're only at 1.7a, so we can start to trace our cardioid. We're going counterclockwise, so we get this. Now we're going to plug in the angle pi over 2. Cosine of pi over 2 is 0, so the value is just 1 times a, so we'll extend the arc going counterclockwise to that point. At the angle 3 pi over 4, cosine is negative, so you see the calculation right here, we get approximately 0.3a. And then finally at pi, cosine is minus 1, so we get a times 1 minus 1, or 0. So let's plot those 2 points and extend the arc there. And then if we continue to be to 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi, we would just get the symmetric version of what we have here in the lower half plane, so we can just put that part on there on the graph. And so you can see why it's called a cardioid. Now, if we want to get the area of that, we're going to use this formula for area in polar coordinates that looks like this. So it has a kind of unfamiliar look to it at this point. Let's contrast that with the area formula that we had or would have if we did a double integral in calculus or using rectangular coordinates. That would just be dx dy. So the question is, why the r dr d theta? Notice that in rectangular coordinates, if we're in the plane, that this distance would be dx, this distance would be dy, so a rectangular unit would be just the product of those two. So what we need to do is investigate why this is the case. And we're going to do that on the next blackboard. So we're trying to find the area of this region on a sector region. And so let's review some formulas. First, the circumference of a circle is 2 pi r, so an arc would just be the prorated portion or the proportional portion of the circle, so it's just theta times r, or in our case, since the angle is going to be d theta, it's d theta times r. So this arc length right here is going to be d theta times r1, and the interior arc length here is going to be times r2, and the interior arc length is d theta times r1. But if we can just assume that this arc, this dr, is very small, then r1 and r2 are going to be essentially the same, and we're going to get d theta times r. So the area of the sector is just going to be how far out it extends, which is dr, multiplied by that arc length, which is d theta times r, and that's how we get the r dr d theta that we saw back here. So let's use this area formula right here to find the area of this cardioid. Oh, I should say one more thing. What about limits of integration? So when we're first integrating dr, and so we're the bottom limit of integration here is going to be how far we are initially out from the origin on the curve. That is just 0, and then how far are we out at the end on the curve? That is our f of theta, which we're going to put in as a1 plus cosine theta. We're going to put it actually in there. And so let's take this integral over to the next blackboard. So when we do a double integral, we do the inner integral first and then do the outer integral. So this inner integral is a dr integral. Notice that the limits of integration here and here are going to convert us to the variable theta once we plug those in. and then I didn't talk about these theta limits of integration. Since we're going all the way around the cardioid, it goes from 0 to 2 pi. So first we're integrating r with respect to dr, and so that would give us r squared over 2, and then we're going to plug in the limits of integration, 0 to a times 1 plus cosine theta. Right, so we've integrated r dr, and that gives us r squared over 2, and we're plugging in the limits of integration. When we plug in those limits of integration, we get this. And notice that when we're squaring this part here, just the a part, that gives us, that is a constant, so we can bring that outside of the integral. The over 2 comes from here. So now we're going to square the 1 plus cosine theta to get this, and we'll take that to the next blackboard to integrate and plug in the limits of integration. So the constant out front stays. We integrate the 1 to get theta. We integrate 2 cosine theta to get 2 sine theta. To integrate cosine squared theta, we use the identity that that's the same as 1/2 1 plus cosine 2 theta. And so when we integrate the 1/2 times 1, we get 1/2 theta. And when we integrate the 1/2 times cosine 2 theta, we get 1/2, and the integral of cosine 2 theta is sine 2 theta divided by 2. And we're going to plug in 0 to 2 pi into all of those occurrences of theta. So let's notice that when we plug in 0 into all of these expressions here, they are all going to be 0, so we don't need to bother with the plugging in of the 0 part, just the plugging in of 2 pi. So we plug in 2 pi theta and get 2 pi, plug in theta to sine theta, or plug in 2 pi to sine theta and get 0, plug in 2 pi to this term here and get pi over 2, and plug in 2 pi to the last term, because it's sine, we get 0. Whoops, this term here, it's 1/2 times 2 pi, so that should have been pi there. So we've got 2 pi plus pi, which is 3 pi, and we get this result, 3 pi times a squared over 2. On the next blackboard, we're going to start to look at the spherical coordinate notation and its usefulness, which actually spherical coordinates are actually more useful in physical chemistry than polar coordinates, because they're three-dimensional. It's a three-dimensional coordinate system. So if we swing over the angle phi and drop down from the z-axis the angle theta, and then move out the distance r, we have the spherical coordinate representation of a point, which would be r phi theta. Conversion from rectangular to spherical is quite a bit more complicated, and here's what we have. You can see some similarities to polar coordinates. The x has the cosine phi on it, the y the sine of phi, and we also have these similar relationships to the polar coordinate to rectangular coordinate system. R equals square root of x squared plus y squared plus z squared, which you could show using some trigonometry, and that tangent of phi is y over x. That's pretty easy to see from these two here, because the sine thetas cancel out, right? The unit of volume, so we use a triple integral to calculate volume. The unit of volume comparable to the unit of area in polar coordinates is a little bit harder to see. It's r squared sine theta dr d phi or d theta d phi. If we label the sides of this volume slice, this side is going to be r sine theta d theta. This side over here is going to be r d theta, which looks just like it did in polar coordinates. And then the thickness here is going to be dr. So that part's not hard to see. This one you have to do some pretty complex geometry in 3-space to see it. So here's what a volume integral looks like. Polar coordinates, I'm just going to set up for a sphere. So we are going, so if we're going to have this be for a sphere, the distance from the origin goes from 0 to a. This is a sphere of radius a. And when we trace out the angles, the angle coming down from the z-axis only needs to go from 0 to pi, because that takes us all the way down to this plane, right? And then, but we have to, in tracing out the phi angle, go all the way around from 0 to 2 pi. So if we pick that up on the next blackboard, we get phi here between 0 and 2 pi, which is just a 2 pi. We integrate sine theta and get minus cosine theta, and when we integrate that between 0 and pi, we get minus of minus 1, cosine of pi is minus 1, and then we're subtracting cosine of 0, which is 1, but because of this minus sign, there's a minus sign here, and then this is from the Von Bell theorem. So that part gives 2, and then we're integrating r squared to get r cubed over 3 between 0 and a, which gives us a cubed over 3. So if we put these three factors together, a cubed over 3, 2, and 2 pi, we get 4/3 pi a cubed, which is the familiar formula for the volume of a sphere. So if we look at this complicated looking function here, f of r theta phi, which is the square of a 2p hydrogen atom orbital, and we integrate that over the entirety of space, let's find out what we get. So the r squared dr and the sine theta d theta and the d phi come from just the setup, and then this part right here is the function that we are trying to see what its integral is. Actually, the integral is going to turn out to be 1, as we'll see, which is the same as saying that this function is normalized over all of 3-space. So we're going to rewrite this to group it together better. So we've grouped the terms, all the r terms together here, all of the theta terms together here, and all of the phi terms together here. So if we write sine cubed as sine times 1 minus cosine squared, we can then let u equal cosine theta. Du is minus sine theta d theta, or minus du is sine theta d theta, and so the integral turns into this. So it turns into the integral between 1 and minus 1 of u squared minus 1, and that integrates to u cubed over 3 minus u between 1 and minus 1, which is, so this and this give us a 2, and this and this are both minus 1/3, so it's minus 2/3, so it's 6/3 minus 2/3, or a result of 4/3. So let's put that back in on our previous blackboard here. And now let's work on the cosine squared phi part. You recall from Calc 1 that we write cosine squared of an angle as 1/2 times 1 plus cosine 2 times that angle. So if we put that in, and then if we integrate the 1, we get phi, and if we integrate cosine 2 phi, we get sine 2 phi over 2, evaluated between 0 and 2 pi. So as we plug in the limits 2 pi and 0, we get 2 pi minus 0 plus 0 minus 0, or a result of pi, and let's put that back in on the previous blackboard. So this integral right here is pi, and now we're going to work on this integral here. So in the front flap of your book you find this formula right here, and that is applicable in our case with with n equaling 5. So that says we're going to have 5 minus 1 factorial as an answer, which is 4 factorial, which means 4 times 3 times 2 times 1, or 24. And so we can put 24 back in that part of the integral we're trying to find. And so if we put all of this together, what we get is, right, if we divide the 3 into the 24, we get 8. 8 times 4 is 32, so all of this part right here is 32 pi, and we're dividing by 32 pi, so that says the 2p hydrogen orbital is normalized. And we're going to do one more of these problems where we show a certain function is normalized. So when we show a function is normalized, we square it and then integrate it over the whole plane. If we square this function, here's what we get. So let's see where everything is coming from. So if we square this, we get the power minus 2r over a0. If we square this, we get this coefficient or constant out front. And then the r squared and the sine r squared dr, and the sine theta d theta and the d phi all come from the setup of the volume integral. So these last two integrals are easy to calculate, right? D phi integrates to phi evaluated between 0 and 2 pi. That's just 2 pi. When we integrate sine theta, we get minus cosine theta, and we evaluate that between 0 and pi, and we get minus 1 minus 1, or 2. And so the product of these two is 4 pi, and now we need to look at this integral right here. So we're going to do this by the substitution technique. We're going to let u equal 2r over a0, and that tells us that r equals minus a0 over 2, du is going to be 2 over a0 times dr, and r squared is going to be a0 squared over 4. So this exponent is u, or the circled part is u, and so we're integrating e to the minus u. Dr is 2, or I'm sorry, d. So dr is, from this calculation here, a0 over 2 times du, and then r squared is a0 squared over 4, and we're still integrating between 0 and infinity, because when we do the transformation between u and r, they're just multiplied by a constant, so the limits of integration stay the same. Let me correct a little mistake here. R, when we solve for r, there's actually a u here, or should be a u here, which makes a u squared here, which means that when we plug in 4r squared and convert it to u, that there should be a u squared here. So what we want to do to clean up this integral is move the constants out. So if we combine this constant and this constant, we get a 0 cubed over 8, which can cancel out with the a0 cubed here, so the constant out front of the integral now becomes what? Just becomes 1 over 8 pi, and then we're only left with integrating u squared e to the minus u du between 0 and infinity. This can be done with this same formula that we used before, but in this case with a u squared, Rn is going to equal 3. So if we move back to here, remember it's if n is 3, then this would be 3 minus 1 factorial is the result. So this integral is, or I should say this bracketed expression is 3 minus 1 factorial, which is 2 factorial, which is 2. So if we plug that in for this as 2, so this part right here is 2, and remember that we have changed this constant out front to 1 over 8 pi. So if we do the multiplication between these four factors, we get that it is normalized over the overall of space, because the integral is 1. So the square of this function, which is the this function here, is just the 1s hydrogen orbital, so it is normalized over all of space. So that concludes this video on chapter 14, where we looked at spherical, or polar and spherical coordinates.